In the last episode, we coded the Big Bang using Python, and this shows light coming from one direction. If we mirror the image, we see light coming from two directions, and this makes a light cone. Well, what's that? Well, this is a space-time diagram, and each point is an event. Events have coordinates t and x. This event will be observed by an observer at the origin 1 year later because it takes light a year to get from the event to the origin. This shows light coming from both directions. The area down here is called the past light cone. Events in this area can affect an observer at the origin in the present, unlike this point, which will get to the observer later. This area is called the future light cone. What's this look like in an expanding universe? Well, let's zoom way out, and we see that space was smaller in the past, and it gets bigger in the future. Let's focus on this quadrant. What is the speed of light in expanding space? Well, if it was c, it would be this straight line. We know that objects in an expanding space move at v equals hd. That's Hubble's law. Since the photon's moving in one direction and the object's moving in another, their relative velocity is c plus hd. But light should be moving at c relative to all observers. We can use this curved line, which is v equals c minus hd, and now their relative velocity is c minus hd plus hd, which is just c, so light is moving at c relative to all observers. And this distance is observed farther back in time. If you watched the previous episode, you could see that we used v equals c minus hd when we actually made this diagram. So how does this actually work? Let's take it step by step. Let's say there's two photons separated by a distance, and that's their wavelength. They're moving at v equals c plus hd as we're going forward in time. The photon on the left is moving at c, but the photon on the right is moving faster. As time goes, that'll keep happening, and the wavelength will continue to increase. If we go back in time, we see a similar picture, but the wavelength is decreasing. So why isn't this equation more well known? Well, it's not as simple as it looks. H is not constant. It was in the previous examples, and that still works, but our universe is more complex. This is the actual equation, and that's simplified too. But more importantly, c minus hd makes it seem like light isn't moving at c. But we know that if light is moving for c at c for all observers, and observers are moving at hd, then its speed has to be c minus hd. This is super simple to implement in an algorithm, even for our changing expansion rate, and it calculates all observables in an FLRW model. Well, what's that? You should check out episode 2 for more details, but it says how much of the universe is matter, how much of the universe is dark energy, and do they add up to 1? If they do, it's flat. We have 30% matter and 70% dark energy in our universe. This just means that triangles have 180 degrees, but when they don't add up to 1, it's open or closed. Our algorithm only works for a flat model, but we can change that. We can add this omega k parameter, and that's going to be defined by 1 minus the difference of the other parameters. We use 1 plus z squared and omega k in our equation, and then we can just use sine or sine h hyperbolic depending on the geometry. There we go. We see that this still uses v equals c minus hd. We can test the algorithm's accuracy by comparing it to cosmology. Well, it's the exact same. You can check out the link in the description to see the notebook if you want. So did I discover the real speed of light? Some may say that this is the coordinate speed of light and not the real speed of light, but the coordinates are the proper distance in cosmic time, which are considered physical time and space. This assumes there's no peculiar velocity and the only motions due to the expansion of space. Well, that's true. There's no length contraction due to special relativity happening. And obviously someone else has pointed out that photons move at v equals c minus hd, but no one seems to have written down this equation or solved it. So, what do you think? Do you know of any examples of this useful equation / algorithm? Got a problem with something I just said? Well, let me know in the comments, and thank you so much for watching.